Now let's design a full adder. A full adder is very useful because it can add three digits, three binary digits. The reason why we need to add three binary digits is because sometimes when a digital system is performing binary addition, it will actually have three digits because one of them needs to be carried over. So what you can do is take this full adder and you can link it to the next one, and then where this one's carrying out, it'll be the carry in of the next full adder. So that's that's far more useful. So you can string together and make a bitewise adder. So in a full adder, you have inputs A and B, which could be a 0 or a 1. And then you have this bit that was carried in, which also can be a 0 or a 1. So there are 1, 2, 3 inputs in a full adder, but the outputs are the same. You either have sum or you have carry. So let's design a full adder. The first step in our design is to notice that there are 3 inputs. So if there are 3 inputs, I'm going to call them A, B, and then let's just simplify things for this video and call this C. In the lecture notes, I type C in just to remind you that it's carry in, but since I'm doing some Boolean math on it, I'm just going to call it A, B, and C. This is a standard truth table for any 3 inputs because the number of lines would be 2 to the n, which is 2 cubed, which is 8 lines. So I made 4 of them 0, 4 of them 1, and then I split that in half. And these half 0, half 1s, half 0s, half 1s. And then I split this in half. I went half 0s, half 1s, half 0s, half 1s. So that's just a regular 3 input truth table. You should all know that by now. If you don't know that, you need to go back to lecture 1. So now let's fill in our truth table. So let's fill in that truth table. So this is just what we had above. This is just any 3 inputs into a truth table are going to look like that. So now we get to do our binary addition. 0 plus 0 plus 0 is 0 carry 0. 0 plus 0 plus 1 is 1 carry 0. 0 plus 1 plus 0 is 1 carry 0. 0 plus 1 plus 1, so 1 plus 1 is 0 carry 1, remember. And 1 plus 0 plus 0 is just 1 carry 0. 1 plus 1 is 0 carry 1. 1 plus 1 is 0 carry 1. And 1 plus 1 plus 1, remember that is 1 carry 1. So these are our outputs to a full adder. Now I know the inputs to the full adder. I know the outputs to the full adder. I can design the circuit. But what are the Boolean expressions for sum and carry? How do I know what the Boolean expression is for sum and carry? Let's do sum first. If this is my output, and these are my inputs, how do I know what expression governs this output? Well, we have a process for that, and that process is called sum of products method. So let's do the sum of products method. Remember the sum of products method. The sum of products method says, circle all of the values with a 1 on the output. Ignore everything else. So we can ignore all of these lines. And we can say that sum must equal, or I'll just do it longhand here. We need to make We need to write down all of the products that make that up. So, and anything that is a 0 is inverted. So this is a sum of products method. And then the Boolean expression that gives us this output is therefore just the sum of all of these products I just wrote down. So sum, or the expression S, is equal to the sum of all these products. And I hope I'm not making any mistakes here, but I'll double check out after I write it down. Okay, so I'm just going to do a double check with my notes here and make sure that I'm not making any mistakes. Okay, so this is correct. That is the expression for sum. And now let's do carry. So in carry, we look at this output and we say, well, what kind of Boolean expression would take these inputs and make this output? Then, well, I have a method for that, and it's called the sum of products method. So to get carry, let's do the sum of products method. So I circle all of the outputs, and I don't care about anything that I hadn't circled, and I write all of the products. And I invert anything that is a 0. And then I add them all together. So carry, you can call it C, is equal to the sum of those 4. And I'm going to double check my notes and make sure that this is okay. And that is correct. So these are the two expressions that govern this truth table. So we have just designed a full adder. Our full adder says if these are my inputs, then these are going to be my outputs. So you can put together this circuit and you will have yourself a full adder. However, that's awkward because these are huge circuits. So what we need to do is try to make these smaller. Oops. Let's try to make these smaller circuits. So let's just simplify the circuits in order to make them smaller. And to simplify this circuit, I can do a little bit of factoring. I notice that A prime exists in both of these. So I'm going to factor A bar out of this first expression. And what I'm left over with are those two terms. And I notice that what's common in this one is A. And I'm going to factor out A. And I'm left with B prime C prime plus BC. Now at this point, I need to notice something. I need to notice that this is, that there is a pattern here. It's a pattern that I said you should always recognize. So this B is inverted, C is not inverted, B is not inverted, C is inverted. That is the exclusive OR pattern you should recognize. And same with here, these are both inverted. The first term is inverted, the second term is not. This is exclusive NOR pattern that you need to recognize. So let's write another line now that we recognize those. This is B, exclusive OR C. And this is B, exclusive OR C, all inverted. Now, I'm going to try to move some of this work. Let's see how that goes. There we go. All right. Okay, please excuse my video. I'm having problems getting my writing tool back. I'm going to pause this video. Okay, I worked out my issues with my my stylus. All right, now I want you to recognize something. You have a pattern again. So let's say A is apples. Let's say B exclusive or C is oranges. You see that apples are inverted here. Apples are not inverted here. Oranges are not inverted here. Oranges are, yes, inverted here. What does that pattern mean? That pattern is the exclusive OR pattern again. Now, you might get upset about that because this is an expression instead of just one single variable or input, but it's okay if it's an expression. It's just a large expression. It still does the same thing. It's not inverted here. It is inverted here. So this is indeed an exclusive OR. So if you don't remember exclusive ORs, please play the video about exclusive ORs. So this is one giant exclusive OR, and on one side of the exclusive OR is A, and on the other side of the exclusive OR there's an expression called B exclusive OR C, and it's okay that there's an expression. It's just a bit more complicated than we're used to. And I don't need brackets, so the end result is A exclusive OR B exclusive OR C, which is indeed the simplified expression for sum of a full adder. And I am having trouble with my device again. So now we have the expression sum is equal to A exclusive OR B exclusive OR C. Now we also notice that the expression for carry is very large. Let's see if we can simplify that. Let's use the trick that we learned in another lecture. And I have a plus ABC here. So I can add another plus ABC here, plus ABC here. That's because x plus x is equal to just x. So I can add as many as any of the terms as I want to. This way I can factor out. In here, I'd have common BC. And then in the next expression, I would have a common AC. And then in these last two expressions, I'd have a common AB. So that's why I want to do that. And what I'm left over with is an A prime plus A from these two terms. And then I'm left with a, let's see, B prime plus B. And then here I'm left with a C prime plus C. And I know this Boolean theorem called X prime plus X, which means it's one or the other is going to be a 1. So the answer is going to be 1. And if you don't remember your Boolean theorems and you say, what is she doing over here? Then you need to go back to the videos about your Boolean theorems. So this turns to a 1, this turns to a 1, this turns to a 1, which is very nice. So then what we end up with is BC plus AC plus AB, not because we're multiplying by 1, but because we have the theorem X and 1 is equal to X. So these are the theorems that I'm using. So I'm going to put this in alphabetical order, AB plus AC plus BC. And this is, yes, the simplified expression for a carry. It's one of them anyway. There's another solution, because if you go to the top of this document and you look at the picture, you don't see that in the picture. So, and if you explore the internet, because adders are very popular, you explore the internet, you'll say, well, I see a full adder 2 different ways. Sometimes I see it like this. I actually like it like this better. And sometimes I see it with an exclusive or in it. So I'm going to say, let's go further and express it with an exclusive or, like the picture above, because that's pretty common too. And then we can draw it both ways if you want to. So if I have C equals, I'm just rewriting it. Then I can and with any one. So if I remember the theory, X and 1 is equal to X. I wouldn't be changing anything if I multiplied by 1. So just bear with me here. I'm going to go AB plus AC times 1. Because I can do that. Okay, and it with 1. Or BC ANDed with 1. And instead of a 1, I'm going to put a Boolean expression that represents 1. B or B prime, so X or X prime is equal to 1. So I'm going to put that in there. And I don't expect you to be able to come up with this. It's pretty obscure. It's a pretty obscure way of trying to get to the other solution for a full adder carry output. There's various ways to do this, and I'm sure that you're going to send me some messages with a much more brilliant way than this. I'm just going to rewrite this a little bit in alphabetical order. Now I'm going to expand. So I can expand A and C across these terms, right? So I'm just expanding, and I'm going to get these. Now I can collect like terms. Here's an AB, an AB, and an AB. So let's factor out AB. If I factor out AB from those, I'll get 1 plus, or C, or C. And some other terms to factor out. I have a C here and a C here, so I'm going to factor out a C, which is going to give me AB prime plus A prime B. Ooh, I see a pattern there. Now, let's look at this. This is 1 or X, or X. Doesn't matter what X is, the answer is going to be 1, right? And then AB ANDed with 1 is obviously just going to be whatever AB is. So therefore, this next line simplified is just AB plus now C bar times a pattern. What is this pattern? Apples not prime, apples prime, orange is prime, orange is not prime. This is exclusive OR. This is A exclusive OR B. And now I have painfully got to the picture that you saw above, how some people like to draw the full adder. There are 2 different ways to draw the full adder, one with this expression and one with this expression. Debatable which one is more simplified. So we have a sum expression in yellow. We have a carry expression in green. In fact, we have 2 of them. Let's put those expressions here. The sum expression was A, oh dear. The sum expression was A, exclusive OR B, exclusive OR C that we developed above from the sum of products method. The carry expression is AB plus AC plus BC, or carry expression is AB or A exclusive OR B, C. So to draw the circuit, we need 3 inputs, A, B, oh, I don't have it on my notes, and C. And we have 2 inputs. I mean, we have two outputs, sum and carry. So inputs A, inputs B, and input C. And I have 2 outputs, sum and carry. Sum is A exclusive OR B exclusive OR C. Carry, I'm going to do it the way I like it first, which is AB or A and C or B and C. Now, A exclusive OR B exclusive OR C. Oops, I need to color code properly. So this first one, what does that circuit look like then? A exclusive OR B exclusive OR C. It looks like this. So A exclusive OR B I'm going to draw that over further. It looks like this. A exclusive OR B. is going to be then exclusive ORed with a C. A exclusive OR B is exclusive ORed with a C. So coming out of here is A exclusive OR B exclusive OR C. And Carrie is going to get 1, 2 OR gates, 1, 2, 3 AND gates, isn't it? So it's going to have 3 AND gates. We're ANDing A and B. So here comes A. And here comes B. Then we're ANDing A and C. So here comes A. And here comes C. And then we're ANDing BC. Here comes B and C. Be careful, don't write A, B, C multiple times. It's only once. Same as when you build this and you plug it in. So now I need to OR the first 2 AND gates together. Here I am ORing those together. Then I need to OR that result with BC. And this we have made a full adder. We have just designed a full adder from scratch. We were given nothing. All we were given is that it has 3 inputs, it has 2 outputs, and it adds. Now let's draw the other way of doing it. So, or we could do sum is A exclusive OR B exclusive OR C, but we could do the other version of carry, which is A, B, or A exclusive OR B, C. And if we did that, we would build it just the same. So we would say, well, we have some inputs. We have A, B, C. For the sum, we'd have A exclusive OR B, which needs to be exclusive ORed with C. So A exclusive OR B exclusive ORed with C would be sum. And then carry needs to take A and B. A and B. So we would have an A and B. Here's my A. And then my B. I would have A exclusive OR B. So again, I need to take my A. I need to take my B. A exclusive or B. I need to AND that with C. A exclusive or B ANDed with C. And all of that gets ORed together. The and the A exclusive or B and C gets ORed together. And this would be carry. And at this point, I sure am hoping that that's the same as what we have above. I'm just thinking that it's probably not, because this is A exclusive or B. And look what I've done here. I've made another A exclusive or B, which is very silly. You wouldn't draw that twice. So what I would do is I would get rid of this exclusive or A exclusive or B, and I would say, well, it already exists here, so I would tie into it. And I would just wire that into that AND gate. So this, I'm hoping, is what we're going to see above. We're going to see, let's see, we're going to see 2 AND gates, and we're going to see 2 exclusive OR gates and an OR. I hope that's what we'll see. If we look at our lecture note above, where I pasted in a full adder. So this is also a full adder. And you can choose which one you build, whether you want to build it with the 2 exclusive ORs, or if you want to build it with all of these AND gates. So let's save our work, and then look above, see if we drew that picture correctly. So here's our full adder. Did we draw this correctly? We have 2 exclusive OR gates. You see they stole from this exclusive OR gate, went into this and that with a C. And then we have an AND gate and an AND gate and an OR. So that's, I believe, what we did below. So we have just designed an entire full adder circuit just by knowing that there are 3 inputs, there are 2 outputs, and the circuit adds. Make sure that you're able to, going forward, design this from scratch. In my final exams, I usually have a students either design a full adder or a half adder entirely from scratch.